In this video, we're going to take a look at a dynamic programming problem called count of subset sum. So basically the problem is that we're given positive integer numbers. Find the total number of subsets whose sum is equal to a given number s. So we have our sum, which is s, and a positive integer array. We want to find the total number of subsets that has a sum that is equal to s, right? So the output is 3. So we have 3 subsets, right? We have 3 combinations. One of them is 1, 1, 2, right? You can see here we have 1 plus 1 plus 2, which will give us a sum of 4. We also can have 1 and 3, so 1 here and 3 here. So that will give us a sum of 4. We can also use another one, right? This one right here plus this 3 right here, right? So we can have duplicate values, but we cannot use the same element twice, right? So in this case, we can have 1 plus 3 and this 1 plus 3 for each and every single combination, right? For each combination, we cannot have duplicate, we cannot use the same element, right? So, but we can be able to have duplicates, right? We can use those duplicate values. And in this case, you can see here we have another example where we have 1, 2, 7, 1, 5, and s is equal to 9. So in this case, we have 3 combinations. So one of them is 2, 7, so 2 plus 7. The other one is 1 plus 7 plus 1, so 1 plus 7 plus 1 will give us 9. And the other one is 1 plus 2 plus 1 plus 5, so that will give us a sum of 9, right? So in this case, we have 3 combinations. So to solve this problem, one way we can do this, we can use a brute force approach. So to do this in a brute force approach, let's say we have s is equal to 3, and we're going to draw the recursion tree out. So initially we're going to have an empty subset, and we're also going to have our capacity because our capacity is 3. So in this case, our initial capacity is 3, right? So we're going to have a capacity of 3. So in this case, we have 2 decisions to make. Either we take the first item, which is 1, or we skip the first item, right? So in this case, we're going to take the current item. If we were to take, then we're going to have 1 in our subset, and the current sum in this case is going to be 2, right? Or the current capacity is going to be 2, right? Or if we skip, then in this case we're going to have an empty subset, and we're going to have a current capacity of 3. And then now we can decide if we take or skip still, right? So in this case, if we take the current item, the next item is going to be 2. And you can see here we found our combinations because now our capacity is 0, right? So because we take a 2, the capacity used to be 2, and now we take an element that's 2, now we have a capacity of 0, so we found our combination, right? So we're going to have a counter and that keep track of the combination. And then we're also going to choose if we don't take this item, right? If we don't take this item, then we can choose to say if we take this item or we don't take the next item, right? So if I choose to take 3, I have a negative value, right? So now 2 minus 3 is going to be a negative value. So we're going to cancel this path, right? And if we found out that this path, right, if we keep skipping, then we have another value that's bigger than in this case, we're going to get a negative capacity, right? So that's also not going to work. So then we can think about this path, right? So what about this path? So in this case, it's the same thing. If I have empty subset right now, right? If our subset is empty, in this case, we can choose to take 2 or we skip, right? But basically at the end, you will see that if we keep skipping, right? And then once we get to this element right here, right? I'll show you. So in this case, we can keep taking this next item, which is 2, right? And then now the capacity is 1, or we skip. So now in this case, we have empty, and we have 3. And the same thing here, we can keep taking the next item, or we skip the next item. But for here, in this case, we can either take the next item. In this case, it's going to be take 3. So we have 3 in our subset, and now the capacity is 0, or we skip, right? So we have skip right here, right? And then here, you can see that we are going to get a combination. So basically, you can see that we have total of 2 combinations at the end. So basically, we're getting a time complexity of exponential. So in this case, to do this in code, I have a class here called count of subset sum brute force, which has an array. And basically in our constructor, we define or declare this array. And basically inside this method, right, we're going to have a solve count of subset sum, which takes an integer value. And it also takes a index that we're going to start, as well as a current num. So then what we're going to do is we're just going to do a recursive approach, right? Basically, we're just going to say if the current sum is 0, that means that we found a combination, then we're going to return 1. If we have a situation where the current sum is actually less than 0, or if the index is actually bigger than or equal to array.length, then that means that we cannot find it, right? Or we should cancel this path, right? Because our path is done, right? So in this case, we can just return 0 because we cannot find any combination. At the end, what we're going to do is we're going to see the total combination if we take the current item plus the total combination if we skip this current item. And at the end, we're going to get the sum between those two, right? So at the end, we're just going to return the sum. And this is going to give us the how many combinations that we can have, or how many total count of subset sum. So you can see here in our static main method, I have a couple examples here. One is 1, 1, 2, 3, and the other one is 1, 2, 7, 1, 5. If I put in 4, I'm expecting 3. And if I put in, so basically if I put in 9, right, if the current sum is 9, I'm expecting 3 as well. So now if I were to run the code for our brute force approach, you can see that our expected result is all 3. So you can see here we are expecting 3. The optimal approach to solve this problem is using a top-down approach. And basically the idea is that we cache the computed result, pre-computed result in a cache, so in a 2D array. And then what we can do is we can be able to retrieve that item if our current situation is already being pre-computed, right? So we're going to have a 2D array, and we're going to have rows is going to be the sum, right? It's going to be the capacity, or the sum the target sum that we want to reach, right, for our current subset. And then for the rows, in this case, it's going to be all the elements that we have in the array. So for the first row, it's going to be the first item. Second row is going to be the second item. And the third row is going to be the third item. And then the fourth row is going to be the fourth item. So in this case, we're just going to compute each and every single slots, right? And if we computed that place before, we can just retrieve that in our cache, right? So you can see here we have a class called count of subset sum top down. Inside here we have a integer array as well as a integer 2D array, and we're going to define the array first. And inside this function, we're going to define the cache, and then you can see here we have n number of rows, n is number of items that we have in the array. And columns is going to be current sum, right? Current sum plus 1, because there could be a situation where we're dealing with 0, right? If we only have 0, the sum is 0, then in this case we want to make sure we find a subset that has a sum of 0, right? So we also have to include 0 there. And in this case we're going to call this helper function. The initial index is 0. We're starting from the first item. And then num is going to be the current sum, right? So, or the current capacity. So if we still have the capacity to take the next item, right? Just like what I said before, if we still have the capacity to take the next item, then we continue. If we don't, then we're going to cancel this path of searching, right? We can just return 0 because we cannot find a subset or a combination, right? And in this case, if we have current sum is equal to 0, that means we found a combination, then we can just return 1. And in this case, if we have a situation where current cache, right, cache at index at current sum does not equal to num, then we can just return cache at index at current sum because we computed that result. So we can just return that, right? And then same thing here, we're just going to search in depth. So if we take the current item, we're going to get the total number of combinations. If we skip this current item, then we're going to get the total combination if we skip this current item. At the end, we're just going to get save the total combinations if we take if we skip onto the 2D cache array. At the end, we're just going to return this result. Okay. So in this case, what we can do is, you can see here we have a main static method, and inside the static method, I create an instance of this class, and I pass in the array, and I pass in the sum, and expecting both 3, right? So at the end, you can see we get 3 and 3. So you can see here the time complexity for using a top-down approach is going to be big O of n times s, where s is going to be number of the value of the sum, right? You can see here we have s number of columns and n number of rows. So the time complexity is going to be big O of n times s, right? And the space complexity is also going to be big O of n times s. So how can we solve this problem using a dynamic programming approach? To do this using a dynamic programming approach, basically what we're going to do is we're going to use the table that we created before, right? We're going to have a 2D array which has a size of n times s. And what we're going to do is, for each and every single position, we're going to get the total, in this case, the total combinations for the current sum for each and every single position. At the end, we're just going to return the total of combinations that we can have for the entire array, as well as the current sum is 4, right? So in this case, we are starting from the top left, and we're working our way down to the bottom right. And in this case, for the first column, we can safe to say that if the sum is 0, the total combinations that we can have is 1, right? If the capacity is 0, that means we found it, right? Just like how we did it in our code in our top-down approach. If we found it, then we can just return 1, right? So in this case, if we found it, then we can just return 1, and this is how many combinations that we can have. Now, if we have a sum that's equal to 1 and the current item is 1, then in this case, the total combinations that we can have is going to be 1, right? Because if I take this item, then now the capacity is 0. So 0 in this case is 1. If I skip, then in this case, then we're going to have 0 combinations, right? So in this case, we're going to have 1. Okay, and then this one, if we have a capacity of 2, or if the current sum is 2, and then we only have one element left, and that's 1. 2 minus 1, we have 1, so there's no capacity. So we're going to be 0 for all of them. Okay, and then what about the second row? In this case, the second row is the same thing. So if I have 1 here, and if I take this current item, then then we have 0 left, right? So 1 minus 1, right? 1 minus 1 is going to be 0. So we have a combination. But if we skip this item, we also get a combination, because if I skip, that means we're going to the previous row, to the next row, to the next item. In this case, we also have a 1. And that also has a capacity, that also has a combination of 1, right? It also has a combination of 1. So 1 plus 1 in this case is going to be 2. So we have 2 combinations for this position, right? If the current sum is 1, and we have 2 items left, and inside our options we have 2 1s, right? Now for this item right here, for this position, in this case, we can also choose to take and skip, right? So in this case, we have to get a sum for if we take this current item or we skip this current item. So if we take this current item, right, and the capacity now is sum is 2, right? So in this case, if I take it, then we have a capacity. In this case, we have a in this case, we're going to have one combination, right? So if I take this item, and then in this case, it's going to be the next item, which has a capacity of 1, right? We only have one item left, and the capacity is 1. Now 1 has one combination, so it's going to be 1. Or if we skip, then in this case, it's going to be 0. If we skip, then we only have 2 and 1, right? So inside our option, we have one item left, and the current sum is 2. So that will now give us a combination. So at the end, you will notice that if we fill out the entire table, we have a pattern. And the pattern is that for each and every single position, we're going to get the total subsets if we take and if we skip, right? This is if we skip, that means it's going to be the previous row. So the previous row's same position, right, is going to be 0. And if we take this current item, then it's going to be the previous row sum minus the current item's value. So it's going to be 2 minus 1, which is going to be 1. So 1 plus 0, in this case, it gave us a sum of 1, right? Just like what we have here. So it's the same for all the elements here, right? So if I were to choose 2 here, and I can use the same formula, right? So cache at index minus 1 at sum, so the previous row, so it's either so 0 plus the previous row sum minus the current element's value. So 3 minus 2 in this case is going to be 1. So in this case, at column 1, right, has a total combinations of 2. So in this case, we have a total combinations of 2 for this position right here, right? It makes sense. If I have a capacity of 3, right? If I have a capacity of 3 and we have 1, 2, 1 in our options, right? We can choose 1, 2 or 2, 1 to be our combinations, right? So that's why at the end we have 2 combinations. So now let's take a look at in our code. And inside our code, you can see we have a DP class. So count of subsets DP. And inside this class, we declare the array. And inside this function, you can see here we have just first we're going to fill the first column with ones, right? When we declare this cache array, by default, each and every single position has a value of 0. So the first column we're going to set to 1. And then for this element right here, basically what we're going to do is that if we notice if the item, in this case, if the current item is if the current item's value, right, the first item in the array is actually less than the sum, then we should be able to set the items to 1, because we know that this sum right here minus the current item will give us a combination. So we set this item to 1 because we know there is a combination. And then we just set it to 1, right? So once we have set all the elements for the first columns as well as the first row, then we can start from the second row and the second column, right? So second row, which is here, and the second column. So we're going to work our way down to the bottom right, and then you can, in this case, you can see here the current item is going to be array I, okay? J is going to be the column, right? So or the current sum. Okay, and then we have skip. If we skip, it's going to be the previous row at the same position, right? If we take, in this case, we want to make sure the current sum is actually bigger than or equal to the current element. If the current sum is actually less than the current element, then in this case, we cannot get current sum minus current element, right? So in this case, that will give us a out of bound. So that's why we do a check here. If the current sum is bigger than the current element, then we can get the difference, right? In this case, the difference in index. Then we're just going to get the pre-computed value, save it on to take. For this current position, we're going to get the sum for if we take and if we skip. Okay, so the total combinations. And at the end, we're just going to return the last element in the 2D array. So if we were to run the code, you can see we're expecting 3 and 3. Okay, so you can see we have expected 3 and 3. So this is basically how we solve this problem. And time complexity in this for using a DP is going to be big O of n times s, where s is the number of elements that we have in our columns, and n is the number of items that we have in our rows, right? Total number of rows that we have in cache. And the space complexity is also going to be the same thing. So if we were to further optimize this, we can use just a temporary variable. We can just use 2 arrays. One is going to be a previous array, and one is going to be the current array. Because all we need for getting the current row, right? To get the data for the current row, all we need is the previous row's data. So if I can complete the previous row's data, I can be able to save it in a previous variable, And if I were to, and based on the previous row and the first item in the array, we can be able to compute these items right here. We can compute the values for those items. And then we're going to save it onto a current array variable. And if we were to move on to the next row, we're going to get the previous row is equal to the current row, right? The current rows array. And then current row is going to be equal to a brand new array, right? Brand new array. So this will give us a time complexity of 2s. In this case, the time complexity is going to be big O of n times s, and the space complexity in this case is going to give us a 2s, right? So we're going to have two array with the size of sum, right? So in this case, if we drop the constant, we're going to have a space complexity of s. Okay, so this is how we solve this problem in a DP or dynamic programming approach.